the three basic programming structures and much of the Java that we need to know in order to write programs effectively. So where do we go here for the rest of the semester? Well, we'll be moving on to looking at techniques used to structure our programs more effectively. We'll investigate some interesting data structures, find out how to handle file input-output, and by the end of the semesters we will wrap up by introducing object-oriented programs. Now remember, loops are used to repeat the execution of a set of instructions called the loop body or the code body, and we set the code body off by a pair of braces. Sometimes we know how many times or iterations we want to repeat the execution of the code body, and we call this the counter-controlled loop. Other times we have no idea on how many iterations will be required. But we do know that we should be on the lookout for some sort of event to occur, and we call this a sentinel-controlled loop. We studied the while loop and learned that the loop would be executed as long as some Boolean expression is true. The other loop constructs we'll be looking at in this lecture also require a Boolean expression to be true in order to continue execution of the loop body. We also discussed the while loop being a pretest loop. That is, that the Boolean expression controlling the execution of the loop is tested before any loop instructions are executed. Consequently, a code body may not be executed at all depending on the condition of the program as it reaches the while statement. So let's take a look at where we're going with this lecture. We'll look at two more variations of the loop structure: the do-while structure, which is a post-test loop, and the for structure, which is another pretest loop, but is preferred in most cases where we need a counter-controlled loop. Sometimes we want to terminate the loop execution before it naturally ends, the Boolean expression becoming false. That's the role of the break and continue statements. And then we'll look at how to determine which type of loop to use and identify some common errors when developing loops. And we'll end by looking at several programming examples. Let's take a look at the do-while loop. Notice that the Boolean expression controlling loop execution is specified at the end of the loop body. Hence, we call this a post-test loop. And the first time the loop condition can be tested is after the loop body has been executed. Therefore, the loop body will be executed at least one time, unlike the pretest loop where the loop body may be executed 0 times. If the Boolean expression in the loop condition is tested as true, control is returned to the do statement. And if the expression is tested false, execution is continued with the statement following the while. The for loop is a variation of pretest loop, and it is the preferred loop to use when we need to implement a counter-controlled loop. Execution generally follows this pattern. We begin by initializing some variable, usually the counter variable that's going to control loop execution. Then the Boolean expression is tested for true, and most often this test involves testing the counter variable. If the expression tests as true, the loop body is executed. If the expression tests at false, execution continues with the statements following the loop body. If the loop body is executed, then the action after iteration iteration is executed, and again, most often this involves changing the value of the counter variable. Be careful in your loop body not to be changing the value of the counter variable. This could have some very strange results in your program. So after we do the action after iteration, then control is passed back to the Boolean expression to be tested again to determine if the loop should continue to execute or terminate. The graphic and the explanation gives you an idea of the sequence of events. Well, let's interpret a for loop code on the right side of the slide. Generally speaking, as long as the counter variable I is less than 100, the loop will execute. But let's see how this starts out, all right? First, I starts as 0. We have initialized I. Then, since I is less than 100, the loop executes. Then we return to the I++, the action after the loop. It's incremented by 1. I is still less than 100. And so we continue this process of executing the loop, incrementing I by 1, testing, and so forth, until I is equal to 100, and then the loop will end. Note that our actions in the parenthesis for the for loop, our actions are separated by semicolons. It's very easy to kind of make a little mistake and use a comma instead of a semicolon. But each of those actions is a separate statement. Let's take a quick look at a trace through a for loop. The first action in this code is I is declared. It's declared outside of the loop, and this is important, and later on we'll see why this is important. Well, the next action is to initialize I, and we set it to 0. Now I is tested. My question is, how many times will this loop execute? Did you say 2? You're right. Once for I equals 0 and once for I equal 1. Since I at this point is 0, the loop body will execute. All right, our body is executed, and we print the welcome message one time. Now control is passed to the after loop execution. I is incremented. Note that this action does not have to be incremented. We could be counting backwards and using a decrement count. And the amount that we increment or decrement by does not need to be 1. It can be any amount that we choose. So if we wanted to display even numbers, we could be doing I plus equal 2. We return to testing the Boolean, and it's still true because I is 1. We print the welcome message once again. We increment I once again, and now the value of I is 2. Back to testing our Boolean, and I is not less than 2, so we'll test as false. The loop body will be skipped, and execution will continue with the statements following the body. Well, we've got a couple of things going on in this first example. Note that I is declared inside the loop as part of the initialization. Consequently, the value of I is only known to the loop. We call this scope. Also notice that the loop body is terminated immediately by a semicolon at the end of the for statement. Consequently, the second system out print line statement is outside the scope of the loop and will always be executed. This is why the statement is marked as a compiler error if you're trying to use I outside of the loop, at which time the compiler is saying I is not defined. Well, taking a look at example 2 here, the action after each iteration in a for loop can be a list of 0 or many comma-separated statements. And in this example, both I and j are being incremented. Therefore, both loops are syntactically correct, but as written, we would probably rarely use those structures in practice. Okay, given a problem here, why don't you stop the video for a minute or so and see if you can write a for loop that will solve this problem. Okay, did you get it? Did you remember to start I at the value of 2 rather than 0, because 0 is not an even number? Maybe is your loop off by 2 because you chose to use a simple less than rather than a less than or equal to. So we have to pay attention to our conditions to determine if the ending value is to be included or not. Well, here's a tricky problem for you. Let's create a loop that's going to count backwards beginning at 0 and go to minus 10. Stop the video and see if you can construct the for loop for this. I told you it was going to be a little harder. Stop the video here and again convince yourself that this is correct. Notice that our action after iteration is decrementing our counter. Well, this error is similar to error we saw in terminating an if body prematurely. And we saw the same error in a slide a little while ago, where I was being used outside of the scope of its definition. The logic error here is that the message, which is outside of the control of the for statement, would only be executed one time, not 10 times. However, we won't even get to execution. Can you determine why? Well, again, we have a scope error. I is declared and known only inside the loop. Consequently, a scope error will cause a compiler syntax error, which the compiler thinks that I has not been defined at this point. So we wouldn't even get to execution. Well, we have a similar type of error here in this while statement. Again, the loop is being terminated prematurely by the semicolon. Should point out that there is no scope problem with the system out or the I++ message, because I is declared outside of the loop. And so we would not have a compiler error at this time, but we'd have a logic error in that our message would only be printed one time. Well, now let's take a look at the do while loop. In this case, we have a semicolon terminating our while statement at the end of the loop, and this is correct. because we have to terminate the do. However, if for some reason you put a semicolon after the do, you would get all kinds of syntax errors because it wouldn't understand where the while was supposed to be matched up. Well, the three forms of the loop statements, while, do while, and for, are somewhat equivalent, and that is you can write the same loop in any of these three forms. For example, a while loop in figure A can always be converted into the following for loop as seen in B. So provided that a while loop is a counter-controlled loop, then we can convert it to a for loop. Well, the for loop in figure C can generally be converted into a while loop as shown in D, except there are some special cases where we can't do this. I'll leave it to you to check review question 3.19 for one of the conditions where we can't convert the for loop to a while loop. In general, my suggestion to you is to use the most intuitive loop or the one that you are most comfortable with using. For loops, use a for loop when you know the number of repetitions and need a counter control loop. A while loop probably is best suited for times when you need to use a sentinel control loop. And a do while loop, again, when you need a sentinel controlled loop, but the loop body must be executed at least one time. Now, on the other hand, while loops and do while loops can be used as counter control. So this problem involves creating a multiplication table. Many of you might have experienced something like this in grade school. I like to think of the problem as developing a set of rows and a set of columns. So that the first row is 1 times 1 times 2 through 9. Second row is 2 times 1 times 2 times 3 times through 9, and so forth. So study the table for a minute and think about how you might create something like this with a loop, and in particularly with a nested loop. Okay, this program appears on page 129 and 130 in your text. You can also find it on Blackboard. I've changed the name of the loop control variables from I and J to row and column. This kind of makes the loops a little bit more understandable for me. Beyond nesting of loops, the program demonstrates a couple of other interesting things. Look at lines 9 and 18. Both lines declare and use a variable named col. How could this be, you ask? We only declare a variable once. Well, again, the issue is called scope. A variable can only be seen and used inside the block of code where it has been declared. So line 9 declares a code block with the for statement. So the first variable col can only be seen inside of lines 9 and 10. Once the loop exits, the variable col no longer exists. And the same is true for the col declared on line 18. When the loop exits on line 21, that col no longer exists and is redeclared when the loop is entered again on line 19. So note the code for the outer loop on line 15 includes lines 16 through 24. So this is controlling the rows of our table. And the inner loop begins on line 18 and ends at line 21. This is controlling the columns of our table. There is code both before the inner loop, line 16, and after the inner loop on line 23. Lines 5 through 12 simply set up the table headings. Line 16 displays a row number and a separator in the left margin. And line 20 displays the bottom of the body of the table. So let's take a look at the next slide. Okay, so what's happening here? Well, the outer loop starts and the row is set to 1. Then the inner loop executes, where col is incremented each time the loop executes until col is equal to 10. So it executes 9 times. Control then is sent back to the outer loop, where row is incremented to 2. Then once again, the inner loop is executed 9 times as the second row of the multiplication table is built. Control is sent back to the outer loop again, and row is incremented to 3. So once again, we're passed to the inner loop. We construct the 3 times row, and control is passed back to the outer loop, and we continue this until the row count is 10. Now, how many times do you suppose the inner loop is executed? Okay, so the code in the inner loop is executed 9 times for each time the row counter is incremented, which means 9 times. So 9 times 9 is 81. So the inner loop code is executed 81 times. We've often talked about the numeric errors involving floating point numbers. They're inevitable, simply because the precision error when working in binary is not exact. This loop gives an example kind of what not to do. Notice that I is declared as a float and is initialized as 0.01 F. The F is needed, otherwise the literal 0.01 would be treated as a double. And note that I is being incremented by 0.01 F. So watch the numeric precision video for a good explanation of what's going on. This video discusses how to minimize these errors. The moral of the story is be very, very careful when iterating a counter-controlled loop with anything other than integer-type data. Well, this is an interesting loop. What do you think? Is this legal? Stop the video. I challenge you to try it and draw your own conclusions as to why or why not this didn't work or worked. Perhaps as a group you might want to start a little discussion on Blackboard. And I'll leave my comments to the classroom. So the problem here is to write a program that prompts the users for a couple of positive integers, and then the program is to find the greatest common divisor between the two. Do you suppose we can do this with a for loop? No, a for loop is not appropriate. We don't know how many times we need to go through this loop. And we also have 2 conditions we need to check. We need to construct our Boolean such that we will continue doing the loop as long as k, our divisor, is less than or equal to both n1 and n2. So it looks like we have some type of while loop. Can you construct the proper condition? So here's the snippet of code that solves the problem. K is initialized to 2 simply because all numbers are divisible by 1, and that would be a trivial answer. We look at the while statement and the Boolean there, and our divisor K is being tested to be less than or equal to both n1 and n2. Now the if statement inside of our while loop is testing that both n1 and n2 are divisible by k, in which case the remainder would be 0. And if the remainder is 0 for both those, then we set our result KCD, greatest common denominator, equal to k. But we can't stop. We have to increment k and find out if there is another divisor that's greater than the one we just set. So the program can be found on Blackboard and on pages 131 and through 133 in your text. So here's the problem. You want to know how many years it'll take before tuition doubles, particularly when tuition is going to increase by 7% every year. And we're going to start at $10,000. So stop the video and ponder the question for a minute. Ask yourself, do I know how many times I must iterate? Is it reasonable to assume that the loop must execute at least one time? Well, how about implementing this solution with a do-while loop? This is a little different than the solution that the book presents on page 133 and 134. But I wanted to demonstrate the do-while, and I think it's reasonable to assume that I have to go through this code at least once if I'm going to double the tuition amount. I've also used some constants to make the program a little bit more user-friendly in case I'm looking to double $20,000 or $15,000. You should note that the result is 11 years, but if you run the program from the book, they initialize the year to 1, and it should be initialized to 0. Otherwise, you'll be off by 1 year. So initialize the year to 0, not 1. So we can control the execution of our loops with a break statement or a continue statement. Break unconditionally ends the execution of the loop, regardless of the truth or falsity of our Boolean expression. Like break in our switch statement, the program continues then executing with the statements following the loop code. Continue, on the other hand, does not terminate the loop. It simply skips over any following code and returns to the top of the loop where the loop control statement is. So if a loop is designed to execute 10 times and it encounters a break statement during the third iteration, the loop exits and is only executed 3 times. If the loop encounters a continue statement, the remaining code is skipped, but the loop continues to execute its 10 iterations. So let's take a look at this first example, testbreak.java. The loop is designed to add 1, 2, 3, and so on to the value of sum. But if we look at the loop body, it's testing to see if sum is greater than 100. If it is, it will break out of the loop. So consequently, as we're adding 1, 2, 3, after we add 14 to sum will be greater than 100, so the loop will terminate, and the loop only executes 14 times. So let's look at this next example, test continue. It is designed to do basically the same thing, add number to sum, but in the loop body we see that we have a conditional there that says if number is equal to 10 or if number is equal to 11 to continue, which means it will skip the sum statement, in which case our sum will be 189 and not 210, which it would have been if we would have added 10 and 11 to our sum. So these two examples kind of give us a look at how break and continue work. Well, program 4.13 on page 137 is our number guessing game. It uses a break statement to exit the loop once the user has guessed a random number. Note that the while statement on line 11 is using while true, which essentially creates an infinite loop, and without the break statement would be doomed to entering a guess endlessly, even when we've guessed the right number. So kind of a hokey way to use break, but it demonstrates the impact of it. Well, a loop is a loop is a loop, and I'm going a little loop-de-de-loop after this lecture.